Hi everybody. So in today's video, we're going to be covering Unit 1, Lesson 7, which is about finding limits by analytic methods. Now we have 3 learning targets for today. The first learning target is I can calculate the value of a limit algebraically using substitution. So we're going to be using algebra and we're going to learn how to use substitution, which essentially means plugging in a number, in order to evaluate a limit. The second learning target today is that we can identify, which means we can determine when it's happening, limits that are what are called indeterminate in form. And the third learning target of today is I can use factoring. So we're going to be thinking back to how to factor to simplify a function in order to determine a limit. Let's go ahead and start with what's called the substitution theorem. So what this theorem says is that the limit as x approaches a number of f of x is always going to be equal to f of c, provided that f of c is a real number. In other words, we can evaluate a limit by substituting the x value that we are approaching into the equation we're given, provided that we get a real number as our answer. Now, when we say get a real number as our answer, we mean you don't want to get something that is undefined. For example, maybe a fraction with a 0 in the denominator would be undefined. If we look at the way this theorem is written, what this means is that we can evaluate this limit by plugging x into the equation. So what I want to do is show you that this theorem tells us that, since this theorem tells us that we can only use this method when we get a real number, I want to show you an example where substituting works, we get a real number, and an example where substitution fails. So let's start with an example where substitution works. If we were asked to evaluate the limit as x approaches 5 of x squared minus 4x plus 3, one option that we've learned already would be we could graph this function. Another option would be we could make a table of values near the number 5. But the easiest way to do it in this case, because we don't have a graph and we don't have a table, would simply be to substitute the value 5 into this equation. So when we do that, what we get is 5 squared minus 4 times 5 plus 3. Now, 5 squared is 25, minus 4 times 5 is 20, plus 3, which gives me 5 plus 3, which is 8. So the value of the limit, in other words, as x approaches 5 on this graph, the y value will be getting closer to 8. Now, an example where substitution fails would be like the following problem. If we were asked to evaluate the limit as x approaches 5 of this function, then using substitution, we would have 5 squared minus 25 over 5 minus 5. Now, if we were to simplify this, we would get 25 minus 25, which is 0, divided by 5 minus 5, which is 0. The reason substitution fails here is because we cannot divide by 0. Later on, we're actually going to learn that this type of limit where we get 0 over 0 is called indeterminate, and there's going to be a special process that we use to evaluate these types of limits. But for now, all we need to really recognize is that in this case, substitution is not an option as far as evaluating this limit. We're going to need other techniques in order to figure this problem out because just plugging in our number didn't work. So what we're going to do next is we're going to go through a few examples where we can use direct substitution to evaluate our limit. Now, the reason we're going through several examples here is that in the past, students have really struggled with evaluating some of these limits because they needed to review their sine functions or natural log functions or logarithm functions. So part of the reason we're going through this process is that I want to review some of the kind of computational techniques that we're going to use to figure out these limits with you. So for problem number 1, in order to find the limit as x approaches 2 of 4x squared minus 3x plus 9, we're going to go ahead and just plug in the number 2. So we would have 4 times 2 squared minus 3 times 2 plus 9. Now, when we evaluate that, we're going to get 4 times 4, which is 16, minus 3 times 2 is 6, plus 9, which means we get 10 plus 9, which is 19, and that would be the value of our limit. For problem number 2, in order to evaluate this limit, we would start by substituting, which means we would have 3 squared minus 4 over 3 plus 3. If we were to simplify this, we would have 9 minus 4, which is 5, over 3 plus 3, which is 6. And that's the value of our limit. For problem number 3, in order to evaluate this limit, we would substitute. Now, as a reminder, e is just a number. It's a number that's pretty close to the number 3. One thing we should remember is that the natural log of e is actually worth 1. So to simplify this, we would have 4 times 1, which is just 4. For problem number 4, we would just substitute first, which is going to give us the square root of negative 5 plus 5. Now, negative 5 plus 5 is 0, so we would have the square root of 0, which is just 0. For problem number 5, we're going to plug in pi over 3, so we would have sine of 2 times pi over 3. Now, that means that we need to evaluate the sine of 2 pi over 3. So to figure that out, you need to kind of think back to the unit circle. On the unit circle, 2 pi over 3 is right here. That's the angle. And the ordered pair there would be 1/2 comma the square root of 3 over 2, and the x would be negative because we went to the left. Sine is the y value, so I would just have the square root of 3 over 2. Finally, for number 6, we would just plug in the number 8, so we would have log base 2 of 8 minus 4. Now, 8 minus 4 simplifies to 4, so we would have log base 2 of 4. And in order to evaluate this, we need to remember that a logarithm is just an exponent. So this is really asking us 2 to what power would equal 4? Since 2 squared is equal to 4, my answer here would be 2. Now, let's go back and talk about what we do when direct substitution doesn't work. So, as a rule of thumb, we should always try direct substitution first. However, if we get 0 over 0 or infinity over infinity, and these could be positive or negative infinities, we are going to call this indeterminate. We are going to learn several algebraic processes that we can use to find the value of a limit that's indeterminate. However, in this unit, we're going to focus on just factoring. So later on, we're going to learn more of these processes, but for right now, we're going to learn one algebraic process that will allow us to find the value of a limit that is indeterminate. An indeterminate limit requires us to manipulate the function using algebraic techniques before trying substitution. So before you can substitute, you have to do some of these things. The three most common techniques are often factoring, multiplying by a conjugate, or simplifying a complex fraction. Now, because later on we're going to learn some of these other techniques, right now we're just going to focus on factoring. So for this unit, all you really need to make sure you review and practice regularly is factoring. Later this semester, we will also study something called L'Hopital's rule, which is named after a man whose last name was L'Hopital, which is another method that we can use to evaluate limits that are indeterminate. But for now, again, we're going to focus on factoring and identifying limits that are indeterminate. So let's connect some of these representations. Let's say, for example, that I asked you to evaluate this limit using substitution. When we substitute, we get 2 squared plus 2 minus 6, and on the bottom we get 2 squared minus 6 times 2 plus 8. Now when we simplify this, 2 squared is 4, plus 2 is 6, minus 6 is 0. 2 squared is 4, minus 6 times 2 is 12, makes negative 8, plus 8 is 0. This limit is indeterminate. And I know this because if your limit is ever 0 over 0 or infinity over infinity, we call that indeterminate. Now let's see how doing a little bit of algebra first can actually allow us to simplify this problem. So same limit, but this time we're going to evaluate it using algebraic techniques to simplify first. Now here's what I mean. Let's say we want to simplify this. I might start by factoring both the numerator and the denominator. So I'm not finding the limit yet, which means I'm going to continue to write limit as x approaches 2 on this next step, because I'm not actually finding the limit, I'm just simplifying the problem. If I were to factor the numerator, I would get x plus 3 times x minus 2. And if I were to factor the denominator, I would have x minus 4 times x minus 2. What you should notice here is that there is a factor of x minus 2 in both the numerator and the denominator. So because of that, we can cancel those factors, which means our simplified limit would be the limit as x approaches 2 of x plus 3 over x minus 4. Now, when we try substituting, so remember, we didn't substitute right away, we just factored and simplified, and now we're going to substitute. Our new problem is going to be 2 plus 3 divided by 2 minus 4. Now, 2 plus 3 is 5, and 2 minus 4 is negative 2, which is a real number. So we were able to find this limit. Now let's compare that to a graphical representation, because we've learned how to find limits on graphs before. If we were to graph this original function, this is what it would look like. There would be an asymptote in this graph, a vertical asymptote. There would be a horizontal asymptote in this graph, and there would be a hole. One thing that I want to remind you is that if a factor cancels from both the numerator and the denominator, it creates a hole in the graph of the function. And this hole is located at the point 2, negative 5 over 2. If I were to evaluate this limit using the graph, because it's a two-sided limit, I would look at both sides as I approach 2. And both sides are approaching this hole. which means the limit value would be the y value, which is negative 5 over 2, which confirms what we got here, negative 5 over 2. Now, here's why we went through this process. If you stuck to just trying direct substitution first, which is our rule, we're going to get an indeterminate limit. One of the techniques we can use to simplify these types of limits is factoring. And when we factor here before we try substituting, after we substitute, after simplifying, we actually end up getting a real answer, which confirms that the limit is actually the location of the hole in the graph. Now, here's a couple notes about factoring. If a factor cancels from the numerator and the denominator, then the function has a hole at that x value. For example, in this problem, the hole was located at x equals 2 because the factor x minus 2 canceled on the top and the bottom. If a factor of the denominator only does not cancel, then the graph has an asymptote at that function, a vertical asymptote at that x value. So an example here would be like x minus 4. So there would be a vertical asymptote at x equals 4, which we can confirm by looking at the graph. Now, if it's a hole, then that means the limit is going to be the same on both the left and the right, and so the limit's going to exist. If it's an asymptote, it kind of depends on whether the function goes the same way on both sides of the asymptote or in opposite directions. So what I'd like to do now is take a look at some problems where we can look at when we might want to simplify and how we might want to show our work for problems where factoring does not help us simplify the problem. So it says evaluate the following limits, show all of your work. For problem number 1, we're asked to find the limit as x approaches negative 2 of this function. And remember, the first option, and the one we always want to try first, is just direct substitution. So to do that in this problem, I would simply substitute in the negative 2, which gives us negative 2 cubed plus 3 times negative 2 squared minus 4 times negative 2 plus 5. Now, when we simplify this, we're going to have negative 8, and then negative 2 squared is 4, so plus 12. Negative 4 times negative 2 is plus 8, plus 5. And negative 8 and the 8 cancel, so 12 plus 5 is just 17. So in this case, direct substitution works. For problem number 2, if we start by trying direct substitution, we're going to get 3 times 2 squared minus 7 times 2 plus 2. And then on the bottom, we're going to have 2 squared minus 4. Now, if we evaluate this, 3 squared is 4 times 3 is 12, minus 14 makes negative 2, plus 2 is 0. 2 squared is 4, minus 4 is 0. As soon as you see in 0 over 0, you need to note as part of your work that this limit is indeterminate. And it's really important to write that on your paper. Part of using some of these techniques is that you need to show why you needed to use that technique in the first place. So saying the word indeterminate is a required part of showing your thinking in this problem. You have to say that before you can do the next step. Now, the next step would be to try to factor, if possible, to simplify before we find our limit. So in this case, if we were to try to factor, we would have 3x minus 1 and x minus 2. On the bottom, we would have x plus 2 and x minus 2. Now, what you should notice here is that the x minus 2 cancels on both the top and the bottom. So what we can do now is substitute the number 2 into our simplified function. which means we get 3 times 2 minus 1 over 2 plus 2. Now, 3 times 2 is 6 minus 1 gives us 5, and 2 plus 2 is 4, so the true value of our limit is 5 over 4. Now, in the next problem, if we try substituting, because direct substitution should always be our first option, we're going to have the square root of 3 plus 1 minus 2 over 3 minus 3. Now, 3 plus 1 is 4, and the square root of 4 is 2. So in the numerator, 2 minus 2 gives us 0, and 3 minus 3 gives us 0 again on the bottom. Again, it's really important that as the part of your work that you show here, you need to note that 0 over 0 is an indeterminate limit. So I'm going to write the word indeterminate on my paper. Now, what we've learned in this unit is to try factoring, but in this problem, there's really nothing that looks factorable. Some other algebraic techniques, which we're not going to really focus on here, would be things like multiplying by a conjugate, which is actually the algebraic technique I might try here. But for now, if nothing is factorable, we're going to say indeterminate, and we're going to stop. We will learn farther down the road that there are other ways to simplify these problems, but for now, we're going to focus just on factoring. Finally, for problem number 4, we're going to try direct substitution because that should always be our first step. So I would have 5 times 3 plus 1 to the 3 halves power. Now, 5 times 3 is 15. 15 plus 1 is 16. So this problem simplifies to 16 to the 3 halves power. Now, this is something we can simplify even further. And the reason I wanted to go through this example is because a lot of students have struggled in the past with simplifying when there are rational exponents. So what I want to remind you is that this dividing by 2, whatever you're dividing by, is really a root. So this is really the square root of 16. And then whatever is here in the numerator, the 3, is really a power to the 3rd power. Now, these are reversible. I could do the cubed first or the square root first. In this case, because square root of 16 is a number that I know, I'm going to do that first. So the square root of 16 is 4 cubed, and 4 cubed is 4 times 4 is 16, 64. There we go. Last but not least, in this video, we're going to talk about finding limits with piecewise functions. When working with piecewise functions, it's important to pay attention to the breaking point of the function. We can use the same algebraic processes to determine these limits as long as we substitute the x value into the appropriate piece of the function. So this idea of direct substitution works with piecewise functions as well, as long as we substitute the x value into the appropriate piece of the function. Let's look at a one-sided limit example, a two-sided limit example, and then a common mistake that I see a lot of. In this case, it says find the limit as x approaches 1 from the left. Now, what I'm noticing here is that 1 is the breaking point of the function. So because of that, the top part of this equation controls the numbers that are bigger than 1, and the bottom part controls the numbers that are less than 1. Since we're approaching 1 from the left, we're talking about numbers that are less than 1. So I would use the bottom part of this equation and then apply direct substitution. When I do that, I get 1 plus 1, which is 2. Now, another example would be a two-sided limit. So if I said find the limit as x approaches 2 of h of x, I would need to check the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. If I wanted to find the limit as x approaches 2 from the left, I would use the top part of this function because those are the numbers for x is less than or equal to 2. And if I want to find the limit as x approaches 2 from the right, I would use the bottom part of this piecewise function because those are the numbers that are bigger than 2. If I substitute the number 2 into the top function here, I get 4 minus 8, which is negative 4, plus 7, which is 3. If I substitute the 2 into the bottom part of the function here, I get negative 4, plus 8, which is 4, minus 1, which is 3. Because these two pieces match, I would say that the limit is 3. Now let's talk about a common mistake. Suppose you were given this piecewise function and you were asked to find the limit as x approaches 2 of g of x. What we should notice here is that unlike in the two previous examples, the x value in our limit is not the breaking point of this function. Let's go back. Here we were asked to find the limit as x approaches 1 from the left, and 1 was the breaking point. Here we were asked to find the limit as x approaches 2, and 2 was the breaking point. But in this case, we're asked to find the limit as x approaches 2, and 1 is the breaking point. In this case, the number 2 is always greater than 1. So the number 2 is always bigger than 1. It's never going to be less than 1. So because of that, even though this is a two-sided limit, we don't need to use both the top and the bottom function the way we did here, because the two sides of the number 2 are all within this domain. If I were to draw this on a number line, if you imagine here's the 0, here's the 1, here's the 2, this function is broken at the number 1, but we're finding the limit as x approaches 2. Both the left and the right side of the function are within the part of the graph that's controlled by x cubed plus 1. So to check these two sides, I can just apply direct substitution, which would be 2 cubed plus 1, which would be 9. All right, thank you guys so much for watching. I appreciate you guys taking notes, and I look forward to seeing you soon.